Hello everyone, my name is Vipin Kumar and welcome to the Foundation of Distributed System Design series. So what if I told you that every major tech company from Netflix to Amazon to Google faces the same impossible choice when building their systems? Today we are diving into the CAP theorem, the fundamental rule that governs how distributed systems work. Further, we will also discuss some real world examples for each use case, the performance impact of the choices that you make, and also some modern nuances, how this will impact the decision making while designing the distributed system. So, what is CAP theorem or Brewer's theorem? The CAP theorem was introduced by computer scientist Eric Brewer in year 2000. It's elegantly simple yet profoundly important. So let's understand the CAP theorem a bit deeper here. So this is a CAP triangle and each corner of the triangle represents a word or letter from CAP. So C-A-P. Now C stands for consistency, where all your servers show the same data at the same time. A stands for availability, where your system stays up and running, always responding to the request. And P is for the partition tolerance, and your system works even when network connection fails. So let's take a look at the CAP triangle and try to find out the possible combinations that we can make in order to selecting these properties. So this is a CAP triangle and we have the consistency, availability and the partition tolerance at the corners of this triangle. Now, the possible combinations that we can make here are CA, AP and CP. CA is for consistency and availability, AP is for availability and the partition tolerance, CP is for consistency and partition tolerance. And there is another possible combination, that is CAP, which is called consistency, availability and the partition tolerance combination. But there is no such system exist in today's world that can support CAP altogether. So so you can have only three combinations here: consistency and availability, availability and partition tolerance, and consistency and partition tolerance. And you can select only two properties only. Imagine you are building a next big social media platform. You have servers in New York, London, and New Delhi. Now, Sarah is in New York, posts a photo. What happens next is totally depend upon the CAP choices that you make. Now, there could be multiple scenarios. Let's discuss these scenarios one by one. So, scenario one, where you prioritize consistency. So, in the same social media app and the same server locations, you prioritize the consistency in your system, which means Sarah's photo does not appear for anyone until all the servers have it. This means if the Delhi server goes down, nobody sees the post until it's back online. Right? Now let's say if you prioritize availability, the photo appears immediately for users connected to the New York server. But users in London might see an older version of Sarah's feed. And now this is a trade-off in action here. So with the CAP theorem, we have got three combinations here. The first combination is consistency plus partition tolerance. So let's understand this combination using an example of a banking system. So like in this case, when you initiate the transfer money from your bank will first update all the databases that it has and then only initiate the transaction for the external bank. So example of such databases which are focusing on the consistency are like MongoDB, HBase, traditional SQL databases in distributed mode. Now the second combination that we have here is the AP, availability plus partition tolerance. So in AP system, we can take the same example again of social media platform, where we have built a social media platform and the servers are located across the world, New York, London and New Delhi. Now, when Sarah uploads her photo in New York, London and New Delhi servers might see a bit delay in her feed to be updated for the followers. So if any of the server goes down from Delhi or from London, it will not impact the New York user's feed because the system will keep working on that on the latest feed. But in New Delhi or in London, the feed will be delayed. So the feed will be based on the stale data, but that still be available. Right? Now, example of such systems, such databases, which are focusing on the availability are the Cassandra, DynamoDB, and CouchDB. The third combination that we have here is consistency and availability. Now, these are kind of a system which are theoretical ones, but rarely used. They are the single server setup, where everything, the application, database, and the processing unit all are onto the single server, which was fine a few decades ago, but I think now we mostly have the distributed system. So this system is a bit theoretical for now and not often used. Now, according to network fallacies, network partition is inevitable in a distributed system, which means you cannot avoid transfer your data over the internet, and all these systems which are distributed across the different locations, they need to sync. So this means the system needs to be, or the databases needs to be connected over the internet. So we cannot avoid the network here. This means P is fixed from the CAP theorem, and you are left with either select C or A. So you have got two choices only now. Either you have the CP system or the AP system. Now let's understand the performance impact of these choices that we are going to make. So CP is the consistency plus partition tolerance. So they are accurate but bit slower because they need to coordinate between all servers before responding. So the servers or the system which focuses on the consistency, they need to be in sync all the time, and that's the only way for them to respond correctly and being consistent. So they compromise the speed and the availability with the consistency, and these kind of systems are required in the banking system. So let's understand this CP using the shopping cart example, where an app, let's say an Amazon app, is trying to make a request to a server, and server just simply fetch the request data from database and respond it back. Now let's imagine one database goes offline. Now in this case, if the request comes in, the system will not respond and the request will fail, because it's a prioritizing the consistency here. Now let's imagine the same scenario for AP. So AP is for the availability and partition tolerance, where it is always available and working fast, but may not be updated all the time. So the same system again, and in this case, if the request comes in and one database is already offline, the request comes in, the server will respond with the stale data and will not fail the request. So the availability here is the primary focus. So Netflix could be one example which can afford to show you slightly outdated continue watching list, because the speed matters more than perfect accuracy for that feature. Now let's see how real companies handle this. Now Google Spanner chose CP. They sacrificed some of the availability for strong consistency in their global databases, because these databases are used for the financial data storage and transactional operations. So financial accuracy was worth the trade-off that they did. Now Amazon's DynamoDB chose AP and focusing on the availability. So they prioritized keeping the shopping experience available even during network issues. You can always add items to your cart and do shopping. Facebook's Cassandra is also following the similar lines, that chose AP, which means focusing on the availability. Your social feed stays accessible even if some servers are lagging behind. A few missing posts are better than no access at all. So these are some of the real world examples which are using the CAP theorem and making the sacrifices that they make based on the use case and the business need that they have in hand. Now let's understand some modern nuances here as well. So here's a plot twist. Modern systems just don't pick one combination forever. They use something called tunable consistency. So let's take an example of shopping. Let's take an example of shopping cart, where you have the product inventory on the website, you have the user reviews, you have the shopping carts. Now the product inventory follows the strong consistency because you cannot oversell. User reviews, it follows the eventual consistency because if it is fine, if there is any kind of a delay in loading the reviews, system can, so it will not impact the core business of the shopping site. And the shopping cart, availability focused. So users should always be able to add items, right? That's the primary goal of there. Now, the consistency we have discussed here is in three parts: eventual, weak, and strong consistency. And the strong consistency has been selected for the product inventory like this one, and also the eventual consistency for the user reviews, right? So it's like having different rules for different part of your system based on what matters most. Now let's understand the tunable consistencies part, the eventual, weak, and the strong consistency through some examples. So weak consistency here is where you write something on the DB, read may or may not see those recent updates. It takes best effort approach but does not guarantee it. Now strong consistency, that guarantees that after a write, every read will see the latest update and the changes are replicated synchronously. Now eventual consistency, after a write, read will see it eventually in some time. Writes are replicated asynchronously here. Now let's do a recap what we have discussed so far and what we have understood through the CAP theorem. So in the CAP theorem, the combination that we have discussed are CAP, so which is consistency, availability, and the partition tolerance. That does not exist because there is no such system in existence that can support all three properties. CA is the consistency and availability. That is a single server setup, and it's very hard to actually scale that. So it's the practical usage is very limited on this one. Now CP is the consistency and partition tolerance. The example is MongoDB. And AP, availability and the partition tolerance. The examples are Cassandra, CouchDB, React. So these are the practical implementations in the real world. Now this is the CAP triangle, where we have the all three properties at the corners of the triangle: the consistency, availability, and the partition tolerance. Now out of these all three properties, you can only pick two properties. P is fixed in distributed systems, so you are left with only AP and the CP, right? These are your only two options. So let's understand what are the basic questions that you need to ask yourself before designing the system. So let's see What happens if your system is temporarily unavailable? Now ask yourself this. If your system is temporarily unavailable, how that will impact you? How that will impact your business? If it is catastrophic for your business, lean towards availability. Partition tolerance will always be there, so lean towards the AP system. Now, what happens if users see outdated information? Now, if it is dangerous for the business or costly for the business, lean towards consistency or lean towards CP system, because you cannot afford inconsistency in your system, because that is going to cost you business wise. Now, third one is, can you use different consistency models for different features? Of course you can. And we have seen the examples of a shopping website where all three parts, the inventory, the cart, and the user reviews, were using the different kind of a consistency combinations there. So this is often the best approach to use, and modern systems generally rely on this one. So the CAP theorem is not about limiting your options. It's about making informed trade-offs. Right? So the CAP theorem teaches us that in distributed systems, perfection is impossible, but understanding trade-offs is everything. Every time you use Netflix, order from Amazon, or scroll through social media, you are experiencing these trade-offs in action. So next time you are designing a system, remember, you can't have it all, but you can choose wisely. So that's all on the CAP theorem. And thanks for your time. And tune in for the more such videos on system design, concepts, and AI development. See you next time. Thank you.